Is Earth really 4.5 billion years old? Let's put this in perspective. If you started counting from 1 right now without stopping even for a second, to reach the number 4.5 billion it would take you around 162 years. So you see, 4.5 billion is a mammoth number. But is our Earth really that old? Early on, after the scientific revolution in the 17th century, scientists already knew enough about layered rocks, fossils, and other clues to make them suspect the Earth was many tens of thousands, perhaps millions of years old. But back then, humans did not know the interior of the Earth was liquid, nor did they understand the process of radioactive decay. Without this vital knowledge, their models and ideas of how the Earth formed were hugely flawed. The first scientific theories of the age of the Earth calculated how long a planet of our size would take to cool and solidify from its initial molten state. By measuring the temperature of rocks and making estimates about the size of the Sun, scientists came up with figures of anywhere from 75,000 to 20 million years old. But there was a big problem with their theories. Because of swirling molten magma inside the Earth and nuclear fusion inside the Sun, the rate of cooling is much slower than you might expect. In other words, the Earth remains much hotter than it would if it had just formed in space and cooled. By the mid-19th century, scientists had developed a better understanding of what the interior of the Earth was like. They knew about the fluid interior and the constant upwelling of magma. Their estimates of the age of the planet changed to the range of tens of millions to hundreds of millions of years old. But there were still two vital parts of the puzzle missing: the constant renewal of the surface of the Earth over millions of years through continental drift, and the theory of radioactive decay. Scientists initially assumed that a layer of rock in the Earth had been there since the planet formed. Eventually, they realized the surface changed, and many rocks on the surface had been melted and reformed. Just looking at surface rocks wasn't the way to calculate an accurate age for the Earth. The final breakthrough came in the late 19th century with the discovery of radioactivity. Scientists discovered certain elements, especially uranium, decayed at a constant rate. They knew that if they analysed, say, a pound of uranium, they could count how much lead had formed inside the lump via radioactive decay. Imagine putting a scoop of ice cream onto a plate and noting that it takes 1 hour for the ice cream to completely melt. Now, the next time you see a scoop of ice cream on a plate, you can measure how much of the ice cream has already melted, say half, and estimate that the ice cream must have been scooped out half an hour ago. The same principle applies to the radiometric dating of rocks. Scientists can figure out a maximum age for the rock and make the assumption the rock cannot be older than the planet itself. The oldest rocks we've so far measured are 4.54 billion years old. The accuracy of the model is refined further by combining our theories of how the solar system